Yes.
Hello, everybody. So my name is Laura Mayorga, and I'm an exoplanet and solar system scientist. So I'm here representing a team predominantly based at the Johns Hopkins Applied Physics Laboratory. And we've been grappling with the question of if Earth was an exoplanet, could we tell whether or not it was habitable or even inhabited? So we've heard a lot at this meeting already, some really great stuff about what's going on with stellar atmospheres, transmission spectra, and the difficulties associated with trying to not only understand the sources of uncertainty in this area, but lots of great ways that people are working to solve those issues. So adding on to what's the impact or magnitude of stellar variability, we also want to understand and characterize the planetary variability as well. So this gets back to sort of the question that was presented earlier with WASP-19, I think it was, of is stacking transmission spectra even going to be effective at bringing out the signals that we want to detect, or is it going to get all muddied up in these variabilities? Because ultimately, we want to detect these biosignature gases, tell if a planet has a surface, oceans, etc. So the real question is, what can we characterize about a planet and what can we not? So here's a simulated Earth transmission spectrum at a distance of 0.03 AU from the Earth, as scaled from the Robinson et al. 2011 work. Here we can see habitability indicators like water, carbon dioxide, as well as disequilibrium biosignature pairs, such as oxygen and methane or ozone and methane. And what we take from this is that you need a broad wavelength coverage to really assess habitability. Rather than focusing on the detection of a singular molecular species, we need them all. And so these features are hundreds of parts per million in this spectrum, but for example, if you take that 2 micron CO2 band, it would be about 20 parts per million or so in the transmission spectrum of TRAPPIST-1e, for example, assuming a clear sky, Earth-like atmosphere. So the question then is, how variable is this spectrum? We have, of course, created several models for what such variability might look like. And so here I'm showing this movie, this variation in the reflected light due to the rotation of the Earth. However, we don't have such a set of transmission spectra for the Earth. So there's been a couple of attempts at this. And for example, one recent one I could highlight is the McDonald and Cowan work that was published recently about an empirical clear sky transmission spectrum of the Earth from 2 to 14 microns. This is using solar occultation measurements. This has been one of the clever ways that we've measured the transmission spectrum of the Earth, but what's still missing is that UV window, which is partially shown here. And part of the optical and the emission of clouds from that does not allow us to understand the variability caused by clouds in the Earth's atmosphere. This is rotating in and out of the annular region that we're actually probing. So those contributions from clear and cloudy regions at various planetary latitudes can cause these variations. Let's see. Oh. On top of these concerns about planetary variability, we've already seen a lot of discussion on stellar variability, star spots, and the like. So I won't go too much back into that here. But the sun, which has long been our point of comparison for other stars in the galaxy, is relatively quiet. But still, here's an example of the transit light source effect on potential Earth-Sun transit as seen by an observer at 0.03 AU away. So on the top, we're seeing relative transit depth, and the bottom is that size of the transit light source effect. So for the same amounts, for varying amounts of activity on the sun, as you can see here. So not only have we seen that they can mimic atmospheric features, but even here on a quiet star, they can't be outright ignored. So this is our know thy star aspect of this. So to tackle these open questions, as was alluded to earlier today, I propose to you a satellite mission to fly out away from the Earth and actually image an Earth-Sun transit. Current spacecraft that are orbiting other solar system planets may be able to achieve that necessary geometry to get an Earth transit, but these instruments were never designed to look at an object as bright as the sun, or they're not even on the ecliptic, so we need something dedicated to do that. Such a mission would allow us to directly measure the impacts of stellar variability and planetary variability, is what I'm showing here in these two little movies, thanks to partially our sun and Earth monitoring instruments that we already have. And for example, POET, as was talked about a little bit earlier today also. So here in the solar system, we know the right answers because we have Earth monitoring satellites. We have, like here on the left of this movie is about water vapor in the Earth's atmosphere. And we've been staring at the sun a long time with, SDO, SOHO, all these sort of space-based and ground-based solar monitoring stations. To touch a little bit up on the point brought up earlier, the question brought up earlier, not only Earth transits, but moon transits, for example, could tell us more about unocculted star spots because the moon's spectrum would be flat. And so it would really let us measure that along with whatever Earth transits we capture to study how that affects that and the planetary variability in question. So we found, as was mentioned a little bit earlier, that the optimal place to put such a spacecraft is beyond L2. So L2 is about 0.01 AU away. And so here at the top upper right, you can see the transit depth in percent as a function of distance from the Earth. And at the bottom here, we show the fractional transit duration. So to optimize for longer transit durations while still maintaining feature size, we find that this 0.03 AU number I've been saying is optimal. Now, by measuring Earth transits, we can also test how effective stacking spectra actually is. So we know from prior work that planets like rocky planets will require more than 40 transits to begin to robustly characterize their atmospheres. Anything basically beyond CO2 and methane will require more than 40 transits. So do we know our detectors well enough to say that we have sufficiently low noise floors in comparison to the signals that we're trying to measure? And observations of the Earth will allow us to test this. So we also add to the know thy star, the know thy planet, know thy detector. Finally, I want to add one more caveat to Earth-like planet transmission spectra, and this is on the topic of refraction. So refraction, the critical refraction floor, if we look at the upper right portion of this diagram here, is set by the distance between the two objects, in this case, the Earth and the Sun, and the sizes of the star and the planet, okay? So as the light rays pass, thank you, as the light rays pass through the Earth's atmosphere, they are refracted towards your observer. And so this refraction in Earth-like planets sets the continuum in a transmission spectrum, and it's restricting the depth in the atmosphere, the depth that you can probe in the atmosphere in the absence of clouds and hazes. So here in the middle panel, effective transit altitude, you can see that based on the distance to the planet, the effective transit altitude you can get down to is reduced. So for Earth-like planets around an M-dwarf, you can see that at these distances, these refraction floors are nearly comparable to here in the Earth-Sun case. So we'd expect something like 14 kilometers from the Earth-Sun analog, and you can get down to about 10 kilometers for an Earth transiting an M-dwarf. So it's also important to understand where in the Earth's atmosphere are those biosignatures that we're looking for, and what kind of cloud variability we can expect at those altitudes. So a satellite mission will allow us to disentangle the effects of patchy clouds in the presence of refraction through clear parts of the atmosphere. And of course, to say nothing about whatever is going on in the sun, behind this is also an effect. So just to wrap up, in conclusion here, an Earth transit observer could potentially solve these open questions that remain, very complementary to Pandora and Poet, which were just discussed. The solar system is the only place where we can translate these resolvable features we see on a planet with the disk integrated, or ring integrated, I should say, observations that we get of exoplanets. And so it's necessary or even critical that we do these experiments here where we have the right answers to make those connections. Thank you, and I'll take questions.
Thank you, Laura. This is very exciting. We do have questions from Slido. So first was Greg Kopp. He asks, do your spectral transmission curves include reflection of planets or moon's surface from the illuminated crescent, which changes with transit position?
Yeah, we would totally expect that, for example, if you were to observe here just outside of transit, that you would get something like ocean glint or look at these sort of crescent phase variations in scattering properties, right? In a transmission spectrum, that would be, or you're really just seeing the annulus of the atmosphere, and so that's not in there. So it's really just like these out of transit effects is where you'd be seeing those, which would also be really interesting to measure, or something that you can measure with such an observer.
Right. Thank you. There's another question on the potential timeline for an Earth transit observer. What would be the timeline for a mission like this? More
Yeah,
or less.
ideally, of course, this is something that I think would be good to fly sooner rather than later. So, of course, we're exploring potential options for submitting to upcoming, let's say, perhaps another Pioneers call that might happen. Or I know that the Apex Mission of Opportunity call is coming up soon. So we're definitely exploring possibilities for that. But at this time, of course, we have not been selected like Pandora has.
Great. There's a question regarding the celestial mechanics of a mission like this. So how to keep, the position of the satellite and observe multiple transits, or you mentioned, for instance, as well, taking transits as a function of distance. Would would this involve stopping, or would this just involve taking transits as you move away?
Yeah, there's definitely a couple of different possible orbits that you could do from L2, for example, or beyond L2, I should say. There's one way you could, if you fly away from the Earth, sort of just in a straight line, you could imagine, or perhaps in some sort of helical pattern or spiraling type pattern, you could induce Earth and Moon transits across the sun. So there's a couple of different possible orbits that could not only get us the sort of varying distances, but also varying the variable geometries that you would possibly want to probe what an Earth-like transit would look like around a sun-like star.
All right. This sparked other couple questions, but we are above the hour. So please take a look at the Slido. Again, excellent talk. So thank you very much.